Right, well, we are the first philosophers, I believe, to speak here. Somewhat happily, I think our talk will be actually very much consonant with the previous talk. And we might, I hope, to be able also a little bit about actually a couple of the questions that came up in question time. Which one are you? Oh, sorry, I'm Frank Arnsenius. That's Kian. Okay, as also stated, I think by the previous speaker, despite some people's misgivings, we are going to be talking about, well, we're particularly focusing on cases where we have infinite universes, although some of our conclusions might also have consequences, or tentative conclusions might also have consequences for finite universe cases. In the end, we're going to end up saying something rather tentative about the issue of the measure problem and Boltzmann brains and Boltzmann babies. In general, one of the problems, or the problem that we're going to be mainly discussing today, is that as soon as you have an infinite universe, and in any particular region of that universe, finite region of universe, you have non-zero chance of observers developing, then if the correlations between disjoint regions go to zero as they get further and further away, we're going to have as a consequence that with chance 1 there are infinitely many observers, and not only that, with chance 1 pretty much any observation, as long as it's not infinitely sharp, will be made. And as soon as you have that, you might think, well, oh, how now are we going to draw any conclusions on the basis of our observations? Because for any observation, after all, there's chance 1 that it will be made somewhere. And you might, in particular, also worry not about comparing different infinite models. You might also think, well, if in an infinite model any observation will be made with chance 1, and in a finite model it won't, aren't we now all at a loss as to how to figure out how our observation confirms the one theory rather than the other? So that's a summary of what I just said. Now let me just give an overview of what we're going to do. We are taking broadly a Bayesian framework. I should also say something about terminology. I think throughout this talk I will use the term credence. I think it's pretty common amongst philosophers to do that, probably not amongst physicists. But credence is basically the same as sometimes also use the notion of degree of belief or personal probability, which is, I think, the same as in the previous talk the first person probability was. So by credence, I will mean the same as first person probability in the previous talk. We're going to start then with some toy finite population worlds examples. Then we're going to discuss easy infinite population worlds, in which, roughly speaking, there is a unique simple measure. And then we're going to go on to hard infinite population worlds, where there are several simple measures just make our prior credences agree to. The main point of this talk is to discuss 4 different attitudes that you could take towards this hard infinite population world, which is sort of a general version of a measure problem. We actually will be arguing in favor, but we won't be giving any conclusive arguments, of the so-called compromiser view that I'll explain later. We'll then, as I say, argue for that. I've already said that. And then we'll very briefly say something about how this relates to the measure problem in cosmology related to Boltzmann brains and Boltzmann babies. And we're going to say that although cosmologists might not have particularly used the terminology in our way of understanding the problems, that we think that common practice in cosmology can actually be justified by what we call the compromiser view. Okay, briefly, Bayesian framework. We claim that a good reasoner can be characterized by a reasonable prior credence function and a reasonable evidence rule. The prior credence function is a probability distribution both over worlds, over where the entire world could be, and over locations in these worlds, or self-locating propositions. The evidence rule is basically a rule or a function that gives you your total evidence at a given time, which will be a self-locating proposition. So you can identify it as a function from a location in a world to a proposition, a self-locating proposition. And then we're going to assume a slightly non-standard version of the conditionalization rule. I mean, most people state conditionalization that whenever you get new evidence, you update your previous credence function by conditionalizing on the new evidence. We actually state it in a slightly different form. We just say that at any given moment, you update the real prior rather than the updated one, and you do that by conditionalizing on the evidence. There's various reasons for this. One of this is that it deals easier with evidence loss. It also deals it's better to deal with self-locating degrees, I believe. For all we said so far, there's no problem yet. If you think that A be some kind of cosmic hypothesis, your conditional prior credence at one time and another time can differ, even if both of, if the hypothesis claims that there are going to be infinitely many observations that correspond to whatever E is.
I know it's a legal question, but I verify there's a similar confusion. Location in space? Or
no, in a whole history of a world. So it includes time. Yeah, no. And similarly, consider two different hypotheses, A and B, both of which claim that the evidence in question will be had by infinitely many observers at infinitely many times. There still can be a difference in these conditional values. So there's no problem in principle now about figuring out, there's no problem in principle yet, about figuring out how one bit of evidence bears on a theory and how two different bits of evidence bear on a theory or two different theories, whether they be infinite hypotheses or finite hypotheses. Okay. We haven't said much yet. Our statement of Bayesianism is very minimal, so now we need to say something about what prior credences functions are reasonable. Some Bayesians, the fully subjective liberal ones, stop here. We don't want to do that because if we stopped here, there would be very little that we could say about the business of how you go about confirming theories, in particular theories with infinite spacetimes. Okay, I've written down an attractor principle, which is actually very similar to your the principle that was sometimes used in the previous talk. Proportion. We're not wedded to it, not even in the finite case, but it is a very natural principle. In fact, there are some things about the infinite case that made us later reconsider whether proportion is that obvious in the finite case. But in any case, it's a very, very natural principle, and it just says, for any reasonable prior credence function C and any qualitative property F that entails that the numbers of observers is non-zero and finite, your credence that you have the property F should be equal to, and let me just explain this notation, that C with a little hat on it is the expectation value according to the prior credence function C. The bit in the corner brackets is a random variable whose value is the number of F observers divided by the number of observers if that's Podewis, and otherwise is defined to be 0. Just to give a trivial application of this proportion in finite worlds, let's call the finite circular road hypothesis the hypothesis that there's a finite number of houses equally spaced around a circular road. Every third house is blue, the others are red. One person lives in each house, no other observers exist. I'm not actually going to go through the calculation because it should be pretty obvious that the previous principle implies that in this case you should have credence 1/3, conditional on this being true, this hypothesis, you should have credence 1/3 that you're in a blue house. It's just you're equally likely to be any of the observers. And the first is, well, no, let's not go through the calculation. Before going to the infinite case, let's make some notes on proportion. proportion by itself allows any prior credence function over qualitative propositions, over worlds, not over locations. It really is only constraining how you should distribute your degrees of belief locations in given worlds. It doesn't say anything about how you should distribute your degrees of belief over worlds. But when you combine it with, well, this again might be more known to philosophers than to physicists, but what philosophers call the principle, which is a rule connecting objective chances to subjective degrees of belief, you get much more constraints, and it has interesting consequences. And we could discuss this later if people are interested in it. You could even say it has some consequences that prima facie seem very unintuitive. We're willing to defend it nonetheless, but it becomes interesting enough to have controversial consequences at that point. But since this is mainly about the infinite case, we didn't want to talk about cases like the incubator in Sleeping Beauty. Also, another thing to note, again, this is probably more familiar to philosophers than physicists. When philosophers talk about cases like the incubator in Sleeping Beauty, they seem to think it's very important that you have exact, complete duplication of experiences. Note that our version of what we call proportion, it doesn't matter whether you have complete duplication. The observers in the different houses might not have duplication of experiences. Something that I think in the abstract we said we would discuss extensively, we're actually not going to discuss at all, but we could discuss in question time, and it did also come up in the previous talk, namely, what the consequences of this principle of sort of equal degrees of belief over all locations that are observers with your evidence, of course depends on what you count as an observer. And in particular, it matters whether you count Boltzmann babies and Boltzmann brains as observers, but it also matters whether you count chimpanzees, anything like that as observers. We're going to skate over that. It's a serious and deep issue about which we do have things to say, but we don't have time to talk about them today. Okay, very simple finite case. Oh, no, first infinite case, sorry. There is an infinite road. It has the pattern 2 red houses, 1 blue, 2 red, 1 blue, 2 red, 1 blue. Each house has 1 observer in it, and there are no other observers. Question, what should your degree of belief be that you are in a blue house? Obvious answer, 1/3. Okay. An argument for this. Suppose that there are unique rational credences x, y, and z for the propositions, self-locating propositions, I'm in a blue house, I'm immediately west of a blue house, I'm immediately east of a blue house, and those are mutually exclusive and jointly exhaustive. Suppose that x, y, and z, these 3 probabilities were not all the same, then I would have to disagree with my neighbor. Suppose I was talking with my neighbor, and so I think it's, say, y, and he thinks it's, my left neighbor, he thinks it's z, and those numbers are not the same, then we would have to disagree about the likelihood that the house that I'm in is blue. And that just seems very strange. If I was forced by rationality to disagree with my neighbor as to how likely it is that my house is blue. That's a justification for accepting this 1/3 answer, which is already, I take it, everybody thought was the obvious answer. You can think of that as an invariance requirement, invariance of the self-locating degrees of belief, invariance under shifts. NA finite shifts in the left or right direction. Okay. Let's state a far more general principle that seems plausible. It's called limiting proportion. For any qualitative property f that entails being in a road world such, which is a world like the one that I had but with different color distributions, for any qualitative property f that entails being in a road world such that there's a well-defined limiting ratio of f observers to observers, the principle says your prior credence that you have property f should be equal to the expectation value of the limit of the ratio of f observers to observers. That's a generalization. You might hope, as we originally did hope, that that principle actually would follow from shift invariance. Okay, that's just a clarification of that notation of corner brackets with the infinity symbol attached to it. We hoped that initially briefly hoped that you could derive this from shift invariance. You can't. In cases of non-repeating patterns, a shift invariance, certain non-repeating patterns, shift invariance doesn't entail this limiting proportion. Okay. Asymmetric road. How long have I had so far? 15 minutes.
Go ahead. I'll take over when you get to the
Okay.
forecast.
Okay, asymmetric road. So you can notice on this slide that there is a point to the right of which you get 2 red, 1 blue, 2 red, 1 blue, 2 red, 1 blue. To the left you get 2 blue, 1 red, 2 blue, 1 red. If you take expanding sequences to get to the limit of the ratios, if you expand really fast to the right, you get close to 2/3 being the limit, 2/3 reds being the limiting relative frequency. If you expand very fast to the left and slowly to the right, you're going to get 2/3 blue. What should we do now? Obvious answer, symmetric. Okay. Note that this relies on there being a metric at all. If there was no metric in this world, it wouldn't be clear what you meant by symmetric. Well, you could do it by counting of house numbers. Okay. So here we have, in some sense, a multiplicity of measures, but it's pretty obvious which one is the most natural one. Generalization to multiple dimensions, expanding concentric n-spheres. Again, now we really need a metric on the world that we're living in. An argument you could give for this is not agreement with neighbors, but agreement with the opposite number. Opposite number, I mean, take the midpoint to the right of which you get 2 red, 1 blue, and the left of which you get 2 blue, 1 red. Let's call opposite. Your opposite number is the guy or the person in the house that's the same distance from the midpoint as you are, but on the other side. That will have a consequence, if you assume that, it has to be a half. Uneven road, same as the previous one, except now it's more spaced out on the right. So we have a metric. If you just go by 1 by 1 by house counting, it's the same as the previous case. But now, of course, if you extend it in metric concentric spheres, you would get a predominance of blue houses, because they're more dense on the left-hand side. And I think it's 5/9 blue if you go in concentric, if you go via concentric circles, say, and if you do it by house counting, equal numbers of houses to the right and equal number of houses to the right, you get a half. So now we have multiple options. Some people might at this point say, well, the obvious right thing measure to apply is the one that uses the metric one, and the other person might say, well, who cares about the distances? What really matters here is the distribution of houses. The metric is somewhat irrelevant. And you could make this world that the metric is completely irrelevant. You could state that it otherwise doesn't matter what the metric is. Okay. Said that. Okay, now we get to the 4 attitudes that we think. We'll say a little bit more about more realistic cases of different possible measures. And now I'm going to say something about the 4 possible attitudes you can take towards this. First possible attitude is the absolutist. We just think, well, one of the measures, one of the simple ones that we can detect is the uniquely rational prior to have. You might already, in view of the previous case, think this is not such a plausible view. We're going to give slightly more examples that might convince you that this is not a plausible attitude to take. Next one is a liberal that says any of the ones, and perhaps all the ones in between. If you think, well, it's a bit weird to think that this is allowed and that's allowed, but the weighted average of the two is not allowed, you close it up under convex combinations. In any case, the main aspect of the liberal says any of the simple ones are allowed, are permissible, reasonable priors. So far, we have no argument against that. The Democrat says, oh, and we'll see in a minute somewhat of an argument in favor of that. We shouldn't our creedal state, our belief state, shouldn't be just a single probability distribution. Rather, one should have an unsharp creedal state, which can be represented by a set of probability distributions. And in this particular case, where there's multiple plausible ones, the set should include all the somewhat plausible ones. And again, you might reasonably think, and close it up under convex combinations. And lastly, what's going to be our favorite view, but we haven't given an argument for it yet, the reasonable priors are weighted average of the simple measures with weights related to how simple they are. So you're going to have a single credence distribution, not multiple ones. We're not going to say that there's a unique correct one, nor are we going to say any ones of the simple ones and the ones in between are allowed. We're just going to say there should be a weighted average. And the weight, although there can be a certain amount of difference or leeway for rational people to have different ones, it should be, the weight should correspond to how simple they are. Okay, let's see. Is this a good point to hand over? Okay.
Can I be heard?
Oh, yes, I can. Great. All right, I'll take over. So just to be clear, those, I mean, we haven't given an argument that those are the only 4 possible attitudes. Maybe somebody will come up with a different approach. We're just looking for a way of reasoning that works and has some generality that applies to these puzzle cases, what we're calling the hard infinite worlds, of which the first example was that uneven road, where there's several simple natural ways of defining a self-locating prior conditional on being in that kind of world. So we've seen one example where that happens, which was the uneven road. Here's another kind of example where it happens. So here we have the original infinite road with just two red, one blue, 2 red, 1 blue. But we've added something, and the thing we've added is a telephone wire. The telephone wire is such that every house is connected to 2 other houses. So you can go sort of in one direction along the wire or another direction on the wire. We're imagining that like each house maybe has a yellow phone and a green phone or something like that. And the wire is laid in this funny snaky pattern. It snakes back and forth. You can define this in all kinds of ways. It snakes around on the road in such a way that when you follow along the wire, you get a different limiting rate relative frequency. And of course, you can do this with infinity, the marvels of the fact that the cardinalities are the same. So it snakes back and forth. So along the wire, it's not red, red, blue, but rather blue, blue, red, blue, blue, red, blue, blue, red. So again, now we have 2 sort of natural, simple ways of defining self-locating priors. If you could either go by frequency along the road, limiting frequency along the road, in which you guess your prior that you're in a red house will be 2/3 and 1/3 for blue. Or if you go with frequency along the telephone wire, you get 2/3 blue, 1/3 red. You can argue that it should be 2/3 red by means of the same argument we gave before, where we're thinking about agreement with your neighbor, your neighbor along the road. If you don't go for that, then you'll be in this strange situation where even though nobody's gone out of their house yet, you haven't seen whether you're in a red or blue house, you have to have a different degree of belief in about the color of your house from your neighbor, who has seemingly all the same relevant evidence. But then again, we can give an argument by agreement with your telephone neighbors that it should be 2/3 blue, 1/3 red. And if you don't go for that, then you're going to find yourself disagreeing with your telephone neighbor about the color of your house. So if everyone is reasoning in the same way, and everyone is assigning a point-like probability, then inevitably you're either going to disagree with your road neighbor or with your telephone neighbor. So you have to get used to this odd situation where 2 people, even though they have seemingly exactly the same relevant evidence, are rationally compelled to disagree about, the color of one of their houses. So this might be taken as a very strong kind of support for either the liberal or the Democrat attitude to this case. So to remind you, the liberal adopts a kind of a mild permissivism. He doesn't think that anything goes in general, or she doesn't think that, but in these cases where there's several simple and natural ways of doing probabilities, the liberal thinks that any of those goes, while the Democrat thinks that this whole point-valued framework should be given up in favor of a set of probability functions framework. So the liberal could say, well, sorry, let's talk about the Democrat first. The Democrat could say, on the basis of the previous slide, well, look, if everyone assigns a point-valued credence, then there's inevitably going to be this weird situation of disagreeing either with your road neighbors or your telephone neighbors. The Democrat will then say, but you shouldn't disagree with any of those kinds of neighbors, and will then draw the conclusion that everyone should have not a probability function, but rather a set of probability functions, because there's nothing to stop a set of probability functions from being invariant both under the shift along the road function and under the shift along the telephone wire function. You can just close it under both operations. Similarly, a liberal could argue that, well, what's really intolerable would be rationally compulsory disagreement either between you and your road neighbors or you and your telephone neighbors. On the other hand, if it's merely, the mere possibility of disagreement between rational people already follows from if you've got any degree of permissivism about what rationality allows. So the liberal will draw the conclusion, well, since there can be no cases where there's compulsory disagreement with other kinds of neighbors, the set of permissible credence functions, the set of permissible priors conditional on this kind of world, the telephone road, must be a set that's closed under both kinds of shift functions. So those are tempting arguments, but we think that they can't be accepted because if you require the set of probability functions in question, either the set of permissible ones or the set that it represents your unsharp creedal state, to be closed under both of these functions, then it's going to have to be a really big and extreme set. Far too big, intuitively much too big, much too extreme. So here's a fact. I'm not going to prove it here, but it's quite straightforward. If you have a set that's in this world, and that's a set of probability functions that's closed both under road shifts in both directions and under telephone shifts in both directions, then it's a very extreme set. For any epsilon greater than 0, your set is going to contain some probability functions where the probability of being in a blue house is less than epsilon, and other probability functions where the probability of being in a blue house is greater than 1 minus epsilon. So basically the set contains if the set at least is also closed under weighted averages, it's going to contain members which assign all probabilities short of 0 and 1 to the proposition that you're in a blue house. So if the liberal says, well, the set of permissible priors has to be closed under both of these functions, the liberal is going to be saying that all probabilities short of 0 and 1 are permissible degrees of belief to have that you're in a blue house conditional on being in telephone world. That seems insane. And similarly, if the Democrat says that, the Democrat is going to have to be saying that you ought to be in this state of utter unsharpness where you're not only is your credence not represented by a point, but like any number between 0 and 1 is equally good as far as you're concerned as a representation of the probability that you're in a blue house. And that also seems insane. Okay, so that argument doesn't proves too much. So we think you're going to have to get used to this phenomenon of agreement with a compulsory disagreement with people onto which you're mapped by something or other. Okay, now here's another case, which we think kind of pushes us in the direction of the compromising view. So in this case, you've got the same kind of pattern, but instead of having a road and a telephone wire, we're going to set things up more symmetrically. So you just have this infinite supply of houses. They don't live in an ambient space of any kind, but you can travel between them. In each house, there's 4 what we're going to call beamers. We're thinking of them as Star Trek type things. There's type A beamers and type B beamers. If you travel along the type B beamers in each house, then you'll get the blue, blue, red, blue, blue, red. And if you travel along the type A beamers, you're going to get red, red, blue, red, red, blue. So there's 2, again, ways of assigning the self-locating priors. Oh, sorry. Instead, I just jacked up the numbers a little bit. I made it be 1,000, 1 in 1,000 red for one, and 1 in 1,000 blue for the others, just to sort of help push intuitions. And we're thinking, yeah, those are the 2 natural ways of doing it, but it seems kind of unreasonable to just plump for one or the other, especially given the kind of overall symmetric role that they play. To have prior credence, to be almost sure that if the world is like this, you're in a red house, so that if you find that you're in a blue house, you take that to be really powerful evidence that the world isn't like this, seems unreasonable, and similarly for being in a red house. Likewise, it seems odd to be in a state of very strong unsharpness where, as it were, part of you is thinking of the evidence that you're in a red or blue house as very powerful evidence against this hypothesis. Rather, the attractive credence in this case seems to be a half. It seems like the whole setup kind of is pushing you towards a half. Well, that suggests that's naturally got by the compromising method, where you take the 2 natural simple ways of assigning priors, and you take the weighted average of them. In this case, it's the plain average of them. And I think that thinking about the attractions of that answer to this case tends to push you in the direction, this is far from being a knockdown argument, of thinking that that kind of compromising attitude, the taking a weighted average attitude, is the way to go in other cases as well. You might think, oh gosh, the compromising view, how is this going to work? After all, even in a world where there's no telephone wire being laid down, you can define all kinds of crazy orderings. And if the world is infinite, then you can get it to, you can get the limiting proportion along an order to be anything that you like. But it's of the essence of the compromising view, as we're imagining it, that it cares about what's a simple and natural measure. Let's say a measure defined in terms of the structure that's actually there. If we're in a world where somebody has laid down a road or laid down a telephone wire, we're allowed to appeal to that in defining a measure. On the other hand, if we're just defining something up, that'll detract a great deal from the simplicity and hence from the weight that the thing receives in the compromising view. Okay, here's one more thing in favor of the compromising view and against these liberal and Democrat views. The liberal and the Democrat, they need to say something about where to draw the line between the measures that are simple enough that they're rationally permissible priors or things that should be in your representer, the set of probability functions that represents your Creedal state. And on the other hand, the ones that are too complex, too arbitrary, too silly to be in there. And it's hard to see a principled way of drawing that line. By contrast, the compromiser doesn't need to draw a line. The compromising position makes use instead of a thing that comes in degrees, a kind of a measure of simplicity which you're going to use to determine the weight. So the compromiser doesn't face this challenge. Here's an example that brings this structure out. Could you tell me when we reach 35 minutes from the time we started, whenever that is? Okay. So, okay, here, this is a bird's eye view. So in this world, we've got a two-dimensional grid of houses, red and green. This is a view from great height. So as you can see, the red houses are congregated on the within a few degrees of north, south, east, and west in the grid. And all the other houses are green. How are you conditional on the world being like this? How confident should you be that your house is red if you haven't looked yet? There's different ways that you could do this. If you take the limit in a sequence of nested circles, then you're going to get, well, the total, you're just going to add up the total angles. And the way I've done it is it's the total of each of these things is 10 degrees. So we're looking at 40 over 360. It doesn't matter where the circles start in the scheme of things. Any starting point is only finitely far away from the center, so it just makes no difference. On the other hand, if you take the limit in a series of squares, then you're going to get that's going to be give you a lower probability for red because in each square you've got all the sort of the corners are dominated by green. If you take the limit in a series of diamonds like this, on the other hand, it'll be higher for red. So this is another of these cases where there's different ways of going. After all, there's actually streets in this grid. You can appeal to them in defining the squares and the diamonds. You can define all kinds of shapes, and in fact, if you take some kind of star-shaped thing like this, you can derive the probability of red arbitrarily close to 1 by extending the stars far out along the red axes, or stars like this, you can drive it arbitrarily close to 0. If you're a liberal or Democrat, you'll have to say something about, well, which shapes are natural enough to be permissible ways of doing of calculating your priors. And that seems pretty hard to do in a non-arbitrary way. The compromising attitude gives a much smoother treatment of such cases. You can define some kind of you merely have to say how the different shapes contribute to the weighted average. You might think that all of our examples have been completely cheesy and silly philosophers' examples. One feature that they all have that does seem quite artificial is that they all feature this infinite connection of people, but there's some person or a small handful of people that are kind of special. So the people who live near the boundary between the dense region and the not so dense region in the uneven road case, the people who are close, spatially close to their telephone neighbors in the telephone case, the people near the center of the cross-shaped pattern in the cross case. And the kind of infinite worlds hypotheses that come up as realistic options in contemporary cosmology don't seem to feature anything like that. They don't seem to feature special people who can say, who can pick themselves out in some finite class by some sort of qualitative description. For example, there probably isn't the tallest person, probably the degrees of tallness increase. For every person, there's a taller person, if there's infinitely many people, so forth. So here's an example that shows that you can have this, this kind of difficulty, the existence of multiple natural simple measures without there being any special person. So in this example, there's a cliff, a horizontal cliff, that's the thick black line, and you've got houses distributed on lines that approach that cliff. So the houses get smaller and smaller and smaller, and the people in them, let's suppose, get smaller and smaller and smaller as you approach the cliff. So there's a line of houses 1 meter from the cliff, a line of houses half a meter from the cliff, a line of houses a quarter meter from the cliff, also a line of houses 2 meters from the cliff, 4, 8, and so forth. So the multiples, the powers of 2 meters from the cliff. And on each house, on each line, we've got a random sprinkling of red houses with twice as many red houses, with the density of red houses doubling at each step. And then we also have some green and blue houses, which we put on, according to the rule that immediately north of any red house, we put in a green house, and immediately north of every green house, we put in a blue house. So the red houses are distributed in this random way, and the green and blue houses are put in on top of that. So there's different ways of assigning. In this pattern, because the things are sprinkled on in a random way, nobody's special. Things kind of look the same to everyone, because remember that people get smaller as they get closer to the cliff. So kind of everyone is seeing broadly the same thing. On any north-south line, the fraction of red houses is a third by construction. On the other hand, on any east-west line, there's a lot more red houses, because you've got the red houses that are put in there, then there's the green houses from the line to the south of that, but there's half as many of them. And then there's the blue houses from the line 2 to the south of that, but there's half again as many of those. So you end up, if you take on any horizontal line, the limiting proportion of red houses is 4/7. So similar, and this is also if you take any kind of sequence of nested rectangles or anything like that, it's going to be 4/7. So that's just an example to show that this existence of multiple natural ways of taking measures does not require the kind of cheesy structures that we had before. In fact, in some ways, that cliff example is fairly close to something that comes up in contemporary cosmology, which I'm now going to, in my amateurish way, say a little tiny bit about before we end. So we'll talk in particular, there's all kinds of infinite world things that come up in the context of cosmology, but eternal inflation is one such thing. In eternal inflation, you've got, this is a diagram that's not to be taken super seriously of the universe. The white is inflating region. As we go up, the scale factor increases to infinity. So we have these the pockets are being formed, and I can't draw all the pockets that would be in this. There should be infinitely many of those non-white paraboloid-like looking things, getting smaller and smaller and smaller as we get towards the top. They're all like one another. Some of them are hospitable, other ones are not hospitable. So here's a hospitable one. This is like our pocket universe. We can distinguish broadly 3 eras within it. There's the hot initial era, that's where the distance from the initial pocket boundary is low. Then there's a mild era, and then there's a cold era. And in these habitable pockets, you're going to typically get, each of these things is spatially infinite because of how the scale factor works. So in the green area, you get observers like us occurring at with substantial density. In the red era, in the black era, you get Boltzmann brains occurring with a very low density. And in the red era, you also get people or observers popping into existence who somehow managed to survive in the otherwise hellishly hot environment that they live in. We're going to call those guys Boltzmann babies. And even within this pocket, there's infinitely many people of all three of these kinds. In the whole world, there's even more people of all those three kinds. So we're in this, the situation that we're familiar with arises that there's several natural ways of putting a measure on such a world. You can't, there's no such thing, because we're dealing here with general relativistic spacetimes, there's no such thing as sequences of larger and larger spheres. The closest general relativistic analog of sphere is already an infinite volume thing, so you can't use it to take these kinds of limits. Cosmologists have come up with a number of ways of putting these measures, measures on such a world. And you know, typically finding out what such a measure, you know, what kinds of things it gives high probability to is a tricky exercise. But some of them have turned out to assign very low probability to evidence anything like ours. So for example, there's a thing called a proper time measure, where essentially you start with a finite thing down at the bottom, and you take sort of rectangles like things going up from that, where the height at any point is proportional to the proper time along a geodesic perpendicular to the initial surface. And it turns out that that one assigns extremely high credence to your being a Boltzmann baby, typically some kind of vestigial observer, just only barely observer-like enough to count as an observer at all, who lives a very short and horrible life under hellishly hot conditions before perishing. That's roughly analogous to the horizontal measure in Cliff that's dominated by red houses. On the other hand, if you look at within every pocket, it seems like, and if you just ignore all other pockets, including its sort of child pockets, there's a case to be made that that on any natural measure, that's going to be dominated by the Boltzmann brains, the people in the black cold area. And if you define the measure on the whole space in a sort of a pocket-by-pocket way, then you're going to get a measure that gives extremely high probability to being a very short-lived, sad person who is surrounded by cold strangeness. How do cosmologists react to these kinds of discoveries? Well, some of them they react in all kinds of ways, but the dominant thing seems to be this, that you don't see very much of people plunking a priori for one of these measures, saying, well, we're not miserable Boltzmann brains or miserable Boltzmann babies, so much the worse for that whole model of what the cosmos is like. You don't also, as far as we can tell, see cosmologists going into these unsharp creedal states where there's no such, where their probability for the relevant hypothesis is represented by some kind of interval that goes very down close to 0 or up towards 1. Instead, the search continues for measures that don't suffer from these pathologies, measures on which experience is more like ours and less like those weird baby and brain experiences are typical. And there are some good candidates out there. And in practice, the way this goes, this investigation looks very similar to any other branch of science where people are using their evidence to explore questions of evidence of what the objective probabilities are, where some probability measures are thrown away on the grounds that they give low probability to our evidence, and other ones are endorsed. So there's a sort of a Mysterian way of thinking about what's going on here. Here's a quote from Tegmark. He says, in reflecting on his own practice here, that according to him, there's some correct measure that nature subscribes to, and we need to figure out which one this is, just as was successfully done in the past for the measures allowing us to compute probabilities in statistical mechanics and quantum physics and so forth. So he's thinking, well, we look around us, we see, well, we're not living the horrible lives characteristic of Boltzmann brains and Boltzmann's babies, so he's thinking, oh, so nature must not subscribe to those measures that give high probability to being a Boltzmann brain or baby. Nature must rather subscribe to some other kind of measure that gives high probability to this kind of thing. Now, we find the metaphysics here extremely obscure. We don't really know what it could mean to say that nature subscribes to this, that, or the other measure. For us, the only question there is which ones are simple, are definable in a simple way. And ex hypothesi, several measures in these cases are defined in a simple way. Some cosmologists, I think, hold out the hope that once we get the true fundamental theory on board, that'll be one of the ones that don't suffer from this pathology where there's only one natural measure, but we don't see any grounds for confidence in that. But we do still think that the practice of treating our evidence as if it was telling us what's the objectively correct measure is justified. And the reason for that is that when you're a compromiser, the way that you respond to evidence is formally just like the way that you would respond to evidence if you thought that there was this fact of the matter about what measure nature subscribes to. So your prior credence is a weighted average of fairly simple candidate measures, but when you conditionalize that on your total evidence, that will in effect increase the weight of all of those components that assigned high probability to that evidence and decrease the weight of the components that assigned low probability to the evidence. In fact, in many cases, it'll turn out that there's one of the candidate measures that assigns vastly higher probability to your evidence than any of the rest. So that in effect, once you've conditionalized on your evidence, the result of conditionalizing your priors on your evidence, and in other words, your credences, are approximately the same as the result of conditionalizing that one measure on your evidence. So it's as if that, having got that evidence, you discovered that that one is the one true measure, although you don't actually have this notion of the one true measure in the play. So that's our conclusion. We think that, in general, simplicity matters. You should look for natural, simple measures that in this case, just as in ordinary non-self-locating epistemology. When there's multiple candidates, you should be a compromiser, take the weighted average. And in general, the vision is that simplicity matters in epistemology, and simplicity turns out to matter in a quite similar way in the epistemology of self-locating beliefs, which is what matters here, to the way it matters in the epistemology of beliefs about the world as a whole. Thanks.
Okay, we're out of time, but if there's one question that is really, really good, then someone can ask it. Bob has a really good question.
I mean, as you clearly seem to be aware, I mean, the basic question you're asking, if you don't put on more structure, is completely ill-defined. I mean, I think the correct point of view is the anarchist point of view, is that it's not a question. Not a question that can be given an answer to. I mean, if you have a measure space that has infinite measure, and you want to consider a subset of that, well, that subset has finite measure. You can assign a probability 0 to that. If the complement of that subset has finite measure, you can assign probability 1 to your subset, and otherwise the probability is completely ill-defined and will depend exactly as you've illustrated on how you take limits. Now, of course, if you have more structure in your measure space, if you have a Riemannian metric or something, and you can define balls of radius r and so on, you can take limits that way, and if those exist, you can use those, and that's fine. The compromiser, if I understood correctly, I think makes no sense at all. I mean, you've got your A and B houses, your red and blue houses. Well, suppose your red houses, actually some, infinite measure subset of those were actually pink. You didn't notice at first. So now you've got actually have three houses. I mean, now if you compromise between those, you'll, because you could take limits in such a way that any one of those could have as close to 0 or as close to 1 probability. If you compromise, you'll assign a probability of 1/3 to those 3 possibilities. Okay, but before you noticed that actually it was a shade of pink that was different from the red, and you thought there were only 2, you would have assigned probability 1/2 to the blue houses. So your probability now has jumped from 1/2 to 1/3 because you realized there was a slightly different shade of color. I mean, you just can't do it. The question is ill-defined. It has no answer.
Is my microphone working?
You can
So I'm not sure you correctly understood what the compromiser view was. The compromiser view was not, oh, you think them all equally likely. The compromiser view was if there's different ways of taking, natural ways of taking limits, then you take a weighted average of that. But the limits, I mean, so once you discover there are pink houses, well, now you need to tell me more about how the pink house is distributed. Once you give me the spatial or the order pattern of the pink houses, then I can tell what the results of taking the natural limited frequencies are.
There are infinite number of natural ways of taking limits. You're going to be running back in the same problem. I think I misunderstood.
If there are infinitely many ways of taking limits that are equally natural that all give different results, yes, then you're sunk.
No,
But we
they don't have to be equally natural. They just have to have some finite amount of naturalness. And if you have infinitely many, their naturalness is bounded from below. You can certainly have.
Oh, if the naturalness is bounded from below, yes, but I don't see any reason
That's
to
true.
believe that.
Well, if they,
I mean, in the road case, there were two obvious natural ways to do it. There weren't other natural ways to do it. We're going to say take the road and a wire case. Well, it's natural to take the road frequency. It is natural to take the wire frequency. But we were not agreeing, oh, because there could have been other wires, therefore there's also other natural ways of doing it. No, there's only two natural ways to do it in that case.
okay. I mean, if you have more structure that you identify, of course, then you can take limits and using that structure and get answers.
Yes, if there's other natural structure, but it all depends on what natural structure is.
It depends on the extra structure. It doesn't, there's not like some general prescription, and there's certainly no prescription for figuring out what the structure is or what the naturalness of the structure is.
Well,
But your answers don't really depend on that, so throw everything else out and figure out what your natural structure is.
You mean, I think you're thinking, figure out how you're going to measure naturalness. It's true that if you're looking for precise quantitative answers, it will depend on how you're measuring naturalness. But that's not specific to this case. We think that in epistemology in general, you're deciding between different theories based on considerations of simplicity and so forth.
I mean, you were talking as if there was a measure space. Measure spaces come from somewhere. We're not God-given a measure space. It comes from
Okay, I'm
somewhere.
going to use my dictatorial powers as the chair to thank Frank and Kian again. And